This is a problem where we're going to determine the pH of a weak acid solution. And so we're going to take 0.0180 moles of acetylsalicylic acid, or aspirin, and put that in 0.54 liters of water at 25 degrees Celsius. And we want to determine first the pH of the solution. So the first thing I'm going to do is write out an equilibrium expression and set up an ice table. Because I may not know the acetylsalicylic acid formula off the top of my head, an easy way to sort of abbreviate this weak acid is just to call it HA. And we're going to put this in some water, and it's going to be in equilibrium with its conjugate base, A-, and H3O+. And so from here we can set up our ice table. And remember, you need to use concentrations in the ice table. So we're given moles and we're given liters. So from there we can calculate the concentration. But right now I'm just going to put 0.0180 moles per 0.05400 liters of solution. So that's my initial concentration of weak acid. And we don't have any conjugate base, we don't have any conjugate base in solution initially, or any acid in solution initially. We don't need to worry about water because it's a liquid. So we know as the equilibrium is achieved, we're going to react some of the reactants to form products. So minus X for HA, plus X for A-, and plus X for H3O+. And then at equilibrium, we'll have this many moles per liter, which is 0.00360 minus X for HA, X moles per liter of A-, and X moles per liter of H3O+. We're given the Ka for acetylsalicylic acid, and that's what we need to use here in this case. We have our weak acid on the reactant side, so we know we need a Ka. Our Ka is equal to 3.3 times 10 to the minus 4, and that's equal to X squared, so our A- times our H3O+, and that's divided by our equilibrium concentration of HA, 0.0036 minus X. So can we assume that X is small in this case? Can we eliminate X from the denominator? In order to check that, we'll take our initial concentration of acetylsalicylic acid, that's 0.0036, and divide it by the Ka, 3.3 times 10 to the minus 4. And we end up with a value of 10.9 or 11, doesn't matter. So anyway, this is less than 1,000. So we can't assume that X is small in this case, which means we need to use the quadratic formula. All right, so let's work on that. Let's take this equation here and kind of highlight that. Let's multiply our denominator by the Ka. So we'll have 3.3 times 10 to the minus 4 times 0.00360, minus X. And then I'm going to equals X squared, set that equal to X squared, subtract X squared from each side, 3.3 times 10 to the minus 4 times 0.00360 minus X squared equals 0. When we multiply this out, we'll have 1.19 times 10 to the minus 6 minus 3.3 times 10 to the minus 4x minus x squared equals 0. So A is equal to minus 1, B is equal to minus 3.3 times 10 to the minus 4, and C is equal to 1.19 times 10 to the minus 6. Okay. Now you use your quadratic formula. Negative b plus or minus the square root b squared minus 4ac, all divided by 2a. And so you can plug and chug away at that, and you should end up with x is equal to minus 0.0013, or 9.4 times 10 to the minus 4. If we go back to our ice table, if x were this negative 0.0013, we would see that we would have negative concentrations for A minus and H3O plus. So we know that that can't be the value, which means that x is equal to 9.4 times 10 to the minus 4 molar. And that's our concentration of H3O plus and A minus, and we're asked to find the pH of the solution. So H3O plus is equal to 9.4 times 10 to the minus 4 molar. To find the pH is equal to minus the log of our H3O plus concentration, 9.4 times 10 to the minus 4. And we should end up with a pH equals 3.03. Okay. So make sure you can get that answer. So the other part of the problem, I'll zoom back in over here, is to find the percent ionization of acetylsalicylic acid. So the percent ionization, I'm just going to abbreviate that as percent I, is equal to the amount of conjugate base, A minus, divided by the initial concentration of weak acid times 100 to get the percent. And so we know that our A minus concentration, we just calculated that over here, that's our X value, is 9.4 times 10 to the minus 4 molar. And our initial concentration of weak acid was 0.00360 multiplied by 100. And we should end up with a percent ionization of 26%.